Impulse is defined as a change in momentum. This is analogous to work in energy. Work is the transitional form of energy. Impulse is a transitional form of momentum. Often given the capital letter J as a vector, we can also write the change in momentum as delta P. And if we expand that out in our current notation, we would say that this would be P prime minus P initial. This is a change in momentum. And it can be calculated as such, so usually you can use this basic equation to define impulse and find the change in momentum. And of course, the momentum would change in a system if the final momentum is different than the initial momentum. But of course, the change in momentum is a function of the object's inertia. And that's the first law of Newton. Newton's first law is the law of inertia. An object in motion will continue in motion unless acted on by a net force, right? And so if an object has momentum, a change in momentum would be the result of a net force. So we can also define impulse as being the change in momentum as a function of force applied for a period of time. In this case, F, force, is defined as an impact. We would say that the impact applied for a period of time results in an impulse. This means that it's possible to expand out the impulse formula as J, which is defined as a change in momentum, but then is also force as a vector times time. And so we see that the force direction results in the change in momentum direction. And oftentimes you'll see this on equation sheets written in this expanded form as the impulse formula. So the impulse really can be calculated in a number of ways depending on the scenario in which you're presented. Now, so far, what we've looked at is we've looked at systems where the momentum is conserved. So in a system, we know that P equals P prime. Now, this is the constant value of the overall system itself. However, when we expand that into one or more objects, like P1 plus P2 equal to P1 after the collision plus P2 after the collision, we say that the total momentum of the entire system is conserved and that this summation is equal to this summation. However, since there was a collision, it's very likely that the first object is now moving with a new speed, and the second object is most likely moving with a new speed, or at least in a new direction. So we can say that while the system's momentum is conserved, the individual objects experience an impulse. And so despite this statement being true, it would also be true that there would be a change in momentum 1, and there would be a change in momentum 2. Right? There would be an impulse for both the first object and the second object. So to take this in pictures, if we had our first object 1 moving like this, and a second object 2, let's say for now stationary, and then they collide, and the first object comes to a stop, and the second object continues off with a new speed. What we see is if, let's assume for this example that all the masses are the same, then of course this mass times velocity and this mass times velocity are the same value, and all of the energy or all the momentum has transferred from ball 1 into ball 2 through the collision. Overall, the momentum of the system is conserved, but ball number 1 has lost momentum and ball number 2 has gained momentum, both of which have equaled a change in momentum. A conclusion we can draw then is that the change in momentum of the first object as a vector must be equal and opposite to the change in momentum of the second object as a vector. Now, this is only true in a closed system where we know that the total momentum of the system is conserved, because any momentum that the first object loses, the second object must gain through the collision, or else momentum would just vaporize. And just like energy, momentum cannot just vaporize. And so in a closed system where we use conservation momentum, we can say that each individual object experiences an impulse. Now, of course, if it isn't a closed system, then it's very possible for an object to change its momentum. Now, the only way that would be is if we have a first law interaction. So if I have one object only and it's sitting stationary, and then after some time we find that original object is now moving with some v prime motion, the only explanation for how the ball could go from not moving at v equals 0 to moving at v prime equal to something is that there must have been an action that occurred from one side to the other. And so if we go and read the problem and realize that this object experienced a force where we pushed on this with some F, and we applied that F over some displacement D, we know that we would apply work, right? And we can think about it in terms of work if we're looking at it in terms of energy. But we also know that in order to travel a displacement, there also had to be a time frame in which this occurred, which means that it's possible to use our equations of motion to go from v equals 0 to v equal v prime over this displacement, find the time, and then apply the force for that period of time. That force applied for that period of time results in a change in momentum of that object, right? In this case, the original object. Now, we can also say if we knew what v and v prime were, then we could also expand this delta p as being p prime minus p, which of course we know is mv prime minus mv. And so if we knew the mass and we knew the final and the initial velocities, it's possible that we could be told the force and solve for time, or if we knew this, we could use the time to solve for the force necessary in order to answer the questions, right? Any outside interaction causes a change in momentum is due to an impulse.